Hello everyone. Today we are going to talk about a tree or graph traversal algorithm called DFS. In another lecture, we talked about BFS, which was also a graph or tree traversal algorithm. So if you still don't know about graph, you can watch my lecture on graph. And as we know, tree is also a kind of graph. So in this lecture, we are going to talk about DFS using a tree structure, and we'll show you how DFS is performed and what is the complexity of DFS. So first, the elaboration of DFS. So DFS means depth first search. So when you are talking about DFS, we have to remember two things. First is the depth. The second thing is this stack data structure. So if you remember from the BFS video, in BFS, we said like we have to remember breadth and queue data structure. So from the intuition, probably you can already make some assumption how a DFS would look like. So in breadth first search, we used to traverse the tree through the breadth, right? Or through the width. Okay. So in DFS, we'll be traversing it towards the depth. That means we will traverse as long as we can go deep, right? And once we are actually exhausted here, then we'll come back and then again go to the depth. And then we'll come back again here and then again go to the depth. We'll come back here, go to the depth, and then from here we'll again go to the depth. Sorry. We'll go to the depth as much as possible. Then again come back and go to the depth. Again come back and go to the depth. Okay. So that means we will traverse towards the depth as long as possible. And this is the principle of depth first search. And because using a stack data structure will facilitate that. So let's see using a stack data structure how we can do a DFS. So as we know, stack is a container, right? It's a container with one side open. So both the push and pop will happen on the same side. So because of that, the last unit in, so this is the first unit in, this is the second unit in, but when you are actually popping, two will be popped out. So last in will cause first out. Right? So that is how a stack works. You have seen it in my stack lecture. If you don't remember it, I would strongly suggest to review it first, the lecture on a stack data structure. So let's see, we start from the root of the tree, right? So we push one into the stack, and we keep on doing this until the stack is empty. So now you pushed one. So push one. And then the stack is not empty. So we pop one, right? We pop one and print it. And then we push the children of one. So for the visualization purpose, we do it from right to left, okay? So we pop 4, you see the children of 1 are 4, 3, and 2. We pop 4, push 4, sorry, and then 3, and then 2, right? The children of 1. Once we have popped 1, we have to push the children of 1. Okay, so now we're done pushing all the children. Now the stack is not empty, obviously you see that, right? stack is not empty, so we keep on popping. So the first thing that we are going to pop is 2, right? So we print 2. Next thing that we have to do is we have to push the children of 2. That is 6 and 5. So we push 6 and 5, right? Okay, so all the children are pushed. Now the stack is not empty, so we have to pop again. We first pop 5, and then we have to push the children of 5. That means 10 and 9, right? Okay, so then we are done pushing the children. Now it's time to pop again. So 9, we pop 9. You see 9 doesn't have any children, so nothing to push. Then we pop 10. 10 doesn't have any children, nothing to push. Then now you see that we have gone all the way to the depth, and now we are actually coming back, right? Because we are exhausted there. So we're coming back. Now we see next, that thing that is going to pop is 6. 6 doesn't have any children, so we are exhausted on that branch. We are so coming back to here, right? And then we pop 3. 3 doesn't have anything, so now we are done. That means we are done with all these, this, and this, right? And you see now that 4 was pushed long time ago. 4 was pushed long time ago, but only now it's getting popped. So we pop 4, and along with popping 4, we do push 4 children, that is 8 and 7. So 8 and 7 are pushed. Next, 7 is popped. And children of 7, 12, and 11 are pushed again. And the last 3 steps, none of 12, 11. So 11 will be popped, 12 will be popped, 8 will be popped. So it will be 11, 12, and 8, right? So that is the order that we are going to traverse the tree. And at this point, the stack is empty. We are done. Okay, so let's go back to the code and see how we can code it in Java. So before we start, we need a tree. So the building block of the tree is a node. The node is going to have a value, integer value. For this example, we are creating nodes of integer, and it has a left child and right child. One thing in the example that I showed you, it was just a tree. It was not a binary tree, but for the code, I'm showing a binary tree. Okay, that means it has 2 children, left and right. And the constructor, you can create a node with a parameter that is an integer value. So a node will be created, and that value is going to be assigned to the node. And initially, the node's left child and the right child is going to be null. Okay. Then, so this is the node class. And then we create a binary tree class. In the binary tree class, what you do is, you see in the main function, we create an instance of the binary tree. And then we create like 6 nodes, node A, B, C, D, E. And for each of the nodes, we create the node with an integer value. So these nodes have been created. Their left child and right child, as you have seen in the constructor, is assigned to null, right? It's assigned to null first, and now they have a value. Each of them only have a value. Now let's make some connections. B is assigned as the left child of A. C is assigned as the right child of A. D is assigned as the left child of B. So basically the tree now looks like this. Okay. And then E is assigned as the right child of B. So B has value 2, and E's value is 10. So you see the right child of B is E. This is E. And F, which has a value of 20, is assigned as the right child of E. You see that here. Okay, there goes our tree. the binary tree. Now let's create the DFS function. So this is the DFS function that I have created, you see. So we start with the node, any node. Obviously, you're going to give it the root node of the tree where we start traversing the tree. And as you know, the tree might be empty. In that case, this thing is going to be null, so there is nothing to traverse. In that case, I have to first check if the tree is empty. If the root is null, I don't do anything, I just return. Otherwise, we initiate a stack because we need a stack to do this in the example that I showed you. And then initially we push, as you have seen, push the initial root node, right? Okay, so that's the thing, that's the initialization part. Now inside a while loop, I will do my operations and I will do it until the stack is empty, right? Okay, so until the stack is empty, what I will do is I will pop one element from the stack, that is, I can say this will, and I will print it. So this is when I say that the node is visited. And then I check if the node has the right child. We actually kept on pushing from the right child to the left child in the example, right? So if the node has a right child, then we push it to the stack. If the node has a left, if the node has a left child, then we push it to the stack. And then we go back again to check if the stack is empty and do the same operation again. So this is exactly how I showed you the example, right? So since we have created the tree, let's call this function DFS. And in this example, the tree that we have created, A is the root node, right? So let's pass the root node into the function and try to run it. Okay. So 1, 2, 4, then 10, 20, and finally 3. Okay, so for some reason, okay, this space was not printed here. So this is what you see. Okay, so now I have showed you how we create a like how we actually program a DFS function, right? Using a stack data structure. Now there is another way to do the DFS using recursive function. So you can watch my video on recursive function. So in a recursive function, it's pretty straightforward. As you know, the recursive function is a function that calls itself, right? Okay, and recursive function actually has to break somewhere. So now the breaking point is when you actually reach a null node, then it's their function, recursive function stops. Okay, so in the recursive function, this is the DFS, another way to do DFS, where you pass a node as parameter. It will check if that node is null or not. If that is not null, then you print the value of the node, which is visiting the node. And then you call DFS again with the left child and DFS function again, DFS recursive function again with the right child. Okay. In case the left child, the node doesn't have any left child, so null will be passed and it won't go through. Or in case the right child is null, you are going to send null in it, but that's not a problem. This function is going to be called again and it's going to break here. Okay, so remember this. Let's do this recursive. Let's try to put it somewhere here. So, okay, so Anyways. Oh, okay. So yeah, another one here. Okay, so this is the DFS recursive function. I don't know how I can do this. Okay, anyways. So the thing, what it does is, let's see if I can push it a little bit. No, not allowing me to. Anyways, that's fine. So basically, I first visit the node, print it, and then I call the function again, the same function again, using my left child and then using my right child. Okay. So let's try to, so a recursive function, actually how a recursive function works, it works with something called a call stack. So if you want to know about more about a call stack, I request everyone to watch a video on YouTube and also read the Wikipedia article for call stack. Very simply saying, a call stack is a when you are actually running your program, uh, the state of the program and the calls are saved in the computer's memory, right? So the compiler actually maintains some kind of a stack itself, a built-in stack, which saves different states of the function call. And that is called the call stack. I'm going to show you how actually this is working. So basically you are calling DFS with 1, right? Okay, let's try to formalize this. Let's see this one. Let's say this is actually very simply, let's write this. So it's like DFS of 1. This is going to do these things. Print, it will first, this is the printing one, right? Print 1, and then it will call, so let's say this is, we are calling this as DFS of, we start with node 1, right? So first thing it will do is it will check if this is null, this node. Obviously, this node is not null. So it will go inside, it will print 1, then it will call the left child, that is 2, right? And then it will call the right child, that is, okay, the example here was for binary tree. So basically it's like 3 times it will call DFS of 3 and then DFS of 4, something like this, right? Okay. So let's see if we do it recursively using the call stack, how it will look like. Basically, we'll call DFS of 1. So in the call stack, it's going to be like this. It will print 1, right? So it will push DFS of 1 into the call stack. And how a DFS of 1 will look like? It will look like this. It will print 1, then it will call DFS of 2, it will call DFS of 3, and DFS of 4, right? So this is, by pushing DFS 1, basically I'm pushing this thing into the stack. Now it's time to the pop from the stack. So first thing I'm going to do is print 1. So that means 1 is visited, done. Next thing that I'm going to do is I'm going to call DFS of 2, okay? Now DFS of 2 is another call, right? So basically you now have to push DFS of 2 into the stack. That is another call. So what DFS of 2 is going to do is going to print 2, and then it's going to call DFS of 5, right? And DFS of 6, right? Okay. Okay, now it's time to pop. So I'm going to pop print 2. That means printing 2 and or visiting 2. So 2 is popped. Then DFS of, and the next thing on the top of the stack is DFS of 5. So I pop DFS of 5, and then this is a function call, right? So I have to push it again. So it will look like print 5, DFS of 9, right? And DFS of 10. Okay. Next, I have to pop. So print 5. The visiting of 5 is done. Next, I have to pop DFS of 9. Now, DFS of 9 is going to be pushed again. What is going to be there? Print 9. And then DFS of null, because it doesn't have any children. DFS of null, right? Okay, so printing 9. Next, it's time to pop again. 9 is visited. DFS of null, it's not going to push anything more because it will check if the node is null and something, right? So it's done there. This is also done. Okay. Next, you see I come back here. This was actually what? This was actually DFS of 5 call, right? Something is remaining there. So something was remaining there. So DFS of 10. So DFS of 10 is going to be pushed here, but you see that. So what is in DFS of 10? Print 10, and then call DFS with null, and then DFS with null, right? Okay. Now pop again. And visit 10. This is going to not do anything. This is not going to do anything. So basically, we're done with this. Next thing that is left is this one. So this was actually part of DFS of 2, right? Now we are coming back to this. So pop DFS of 6. Pop DFS of 6. And so we popped it. Now push DFS of 6 call. So this print 6 and DFS of null and DFS of null, right? Now time to pop, print 6. Nothing is there. Nothing is there. So we are done here. Only now we come to the DFS of, okay, next thing to pop. What is the next thing to top? DFS of 3, right? So DFS of 3 is going to be put here. It only does one thing, is just prints 3, right? And other things are like, it doesn't have any children. Okay, so next thing is popped is, this is popped. 3 is visited. Now, what is it in top of the stack? This thing, DFS of 4, right? This one came from the initial DFS of 1 call. Do you remember that? Okay, so this is from the call stack. Okay, so this is popped. Fine, this is popped. And then this is a function call. So we actually push it. This does a print. And then it calls DFS of 7 and DFS of 8. Right? Okay, so next, print 4, done. Next thing that is in it is DFS of 7. So push DFS of 7 call, DFS of 7 call. What it does is print 7, DFS of 11, and DFS of 12, right? So I will stop here. You can just simulate the rest of it. But now you have an idea how a recursive DFS call, right? A recursive DFS call where you actually call the DFS function first, and then you check if the node is null, and then you print the node, and then call the children. Call the same DFS recursive call for the children, right? So now you see how a recursive DFS function call works. Okay, so the code here is for a binary tree, whereas the example that I showed you here is just a tree. It's not a binary tree. So instead of just left and right, you just call on DFS on how many children you have. And you can also visualize how a call stack works. So using a default stack, built-in stack, how the states of the call are saved and then executed when the time comes. Okay, so there goes both the ways to do DFS. The first one that I showed you using exclusive stack, that one is, you can call it the iterative way. So this is the recursive way, right? This is the recursive way. And the first one that we discussed, so using an external stack. So this one you can say this is an iterative way. And this one is a recursive way. Okay. Okay, so next, let's talk about the complexity of DFS. So as you see, every node in the, if you look at the iterative way, every node is actually pushed into the stack once. It pushed once, right? And then popped once. That means if we have like, if the number of vertices are this, we can say the order of the, so the time complexity is order of V. This is the number of vertices, okay? So even if you do recursively, this is the same thing because you visit every node only once. Okay, so that's it for DFS. We'll come back with a new topic in our next discussion. Thank you.